Let's talk about another bonding theory. Let's talk about molecular orbital theory. Why do we need another bonding theory? It's because there are shortcomings. We saw it with valence bond. There's also shortcomings with hybridization, in that it doesn't predict all the physical properties that we see in molecules. For example, diatomic molecular oxygen is paramagnetic. Remember, that means it has unpaired electrons. And from a hybridization standpoint, those electrons ought to all be paired, in which case it ought to be diamagnetic. And so we've got to have a theory that explains this, what we actually see in nature. And so molecular orbital theory comes into play in order to explain that. And we're going to build on some of the concepts that we've used before. Remember, orbitals can hold a maximum of 2 electrons. And these orbitals are going to be a little bit different. Beforehand, the orbitals were all properties of an individual atom. In molecular orbital theory, the orbitals don't belong to individual atoms. Molecular orbitals belong to the molecule as a whole. So mathematically, we're going to come up with these new molecular orbitals, and some of the principles that we've used before. The number of orbitals must be conserved. That means the number of orbitals we start out with, the number of atomic orbitals, is going to equal the number of molecular orbitals when we finish up. When we go about filling these orbitals, putting electrons in these orbitals, lower energy orbitals are filled first, and Hund's rule is to be obeyed. That when there are degenerate orbitals, orbitals of equivalent energy, the electrons will remain unpaired. So let's look at the simplest of molecules. Let's look at diatomic molecular hydrogen. We've got 2 hydrogens. Remember, their electronic configuration is 1s1. So what we're going to do is we're going to bring in these 2 hydrogens. So I've got a hydrogen and a hydrogen with their atomic orbitals. And they each have 1 electron. And so we want create these molecular orbitals that are a property of the molecule as a whole. When we do that, we're starting out with 2 atomic orbitals. That means we're going to wind up with 2 molecular orbitals. One will be of lower energy. Remember, lower energy is a desired outcome in physical processes. And that electron density will be along the internuclear axis, and it will be directly between the atoms. And so this is going to be a sigma bond, and we'll actually call it an orbital, a bonding orbital. This is going to be a sigma 1s bonding orbital. At the same time, we're making an orbital of higher energy. That's going to be an antibonding orbital. We'll call that sigma 1s star. That star represents that it's an antibonding orbital. It's of higher energy. And the s electron density lies along the axis of the nuclei, but it's actually outside of the two nuclei. It's not in between them. And so it doesn't give rise to bonding. And so we're going to put our electrons into these we're going to transfer them from the atomic orbital, this molecular orbital in essence. And we've got 2 electrons that go into the sigma 1s bonding orbital. And so we can come up with something that's called the bond order. And the bond order is equal to 1/2 of the number of bonding electrons minus the number of anti-bonding electrons. That's equal to bond order. So I've got 2 bonding electrons that are in the sigma 1s. I've got no electrons in the antibonding orbital, the sigma 1s star. So 2 minus 0 is 2, half of 2 is 1, is bond order of 1. And lo and behold, if we were to draw a Lewis structure, there's our diatomic molecular hydrogen with its single bond. Let's look at He2. And you might be scratching your head as I say that. You say there's no such thing as diatomic molecular helium. It's a noble gas. And you're right. And so we're going to prove that, quote unquote, if you will, by using molecular orbital theory. So once again, we've got our energy diagram. We've got our heliums coming in. And each one has this 1s orbital that we put 2 electrons in. These are our atomic orbitals. And so we're going to take those atomic orbitals that belong to the atoms individually and make molecular orbitals belong to the molecule as a whole. So we're going to have a sigma 1s bonding orbital and a sigma 1s star that's antibonding. So we start out with 2 atomic orbitals. You have to wind up with 2 molecular orbitals so that the number of orbitals is conserved. I've got 4 electrons to now put into this molecule. 1, 2. They go on the lowest available energy level, so you're on the sigma 1s to begin with, and we pair them up. And then 3, 4. The next electrons go on the sigma 1s star. And so just visually, you can see that the antibonding electrons cancel out the bonding electrons. Or we can go back to our formula of 1/2 the number of bonding electrons minus the number of non-bonding electrons. So 1/2 of 2 minus 2, 1/2 of 0 is 0. And there's no such thing as diatomic molecular helium because it has a bond order of 0. But we can predict the existence of this ion, He2+. Here's our energy diagram. I've got 1 helium that's got 2 electrons, and I've got a helium plus that only has 1 electron. So these are my atomic orbitals. And now I want to create my molecular orbitals. One is bonding, sigma 1s. The other is antibonding, sigma 1s star. We put in electrons in the lowest available energies levels, 2 in the 1s and 1 in the sigma 1s star. And so if we did the bond order, 1/2 of the number of bonding electrons is 2. There's 1 antibonding electron, so 2 minus 1 is 1. 1/2 of 1 is 1/2. And so this is a permanently existing species, but on a temporary basis, we do find He2+ with a bond order of 1/2. And molecular orbital theory allows us to do that. Let's look at Li2. you could call this dilithium if you wanted to. And if you ever watch the really old Star Trek episodes with Captain Kirk and Mr. Spock and Scotty will talk about the dilithium crystals. And according to molecular orbital theory, there could be such a thing. So lithium, remember it's 1s2, 2s1 if you look at the periodic table. So we can look at the atomic orbitals. We're just looking at the valence electrons. We don't care about the inner core electrons because it's the valence electrons that participate in bonding. So we have our two lithium atoms, each with a single 2s electron. And we're going to make a bonding orbital that's going to be a sigma 2s, and an anti-bonding orbital that's going to be a sigma star 2s. That's of higher energy. The sigma 2s is of lower energy. And so we got two electrons that go into the lowest available energy level. And so the bond order will be one half of the two bonding electrons minus no antibonding. Half of 2 is 1. And so dilithium is certainly a possibility according to molecular orbital theory. Let's go to the next element, Be2. Beryllium, 1s2, 2s2. And so if we're looking at energy and looking at the atomic orbitals, all we care about are these 2s orbitals from each of these beryllium atoms. So they each have filled 2s orbitals. We're going to make a sigma 2s and a sigma star 2s. 4 electrons go on the lowest available energy. Pair them up as you go along. And so just visually you can see that the antibonding cancels out the bonding, or 1/2 of 2 minus 2. 1/2 of 2 minus 2 is 0. And so we won't see Be2 according to molecular orbital theory.